So it's my pleasure to talk about energy efficient buildings today, but also buildings that are high performing, which I will expand on a bit later. So as mentioned, I'm practicing energy efficient and green building consultancy in Malaysia, and I've been here now for 16 years doing so. Right off the bat, I just wanted to show some of the projects we've done and show some measured energy consumption compared to the energy consumption of normal office buildings. So if you look at the chart here, this is the gray bar is the energy consumption of normal office buildings, and the unit is basically how many kilowatt hours of electricity they consume per square meter of floor area per year. And these four buildings, some of which I'll talk about today, show that we can substantially reduce the energy consumption, and that it can be done in a way where you actually also have a good payback time. So if you do it right, the extra cost that you spend on building these buildings efficiently will be paid back after 3 years from the reduction in the energy cost. The one with the stippled line here is a retrofitted project. So the measured energy consumption before and after is shown here. And these are not simulated values. These are all from the energy bills of these buildings. So I'll start out, I'll show a new build project. I'll show a retrofit project, both offices, and then I'll finish off with this factory in the forest, which is also a newly built factory that has won a lot of awards lately. So the first building is the Diamond Building, and this is the Ministry of under the Ministry of Energy in Malaysia. It's the Energy Commission. And for this project, we were involved from the very beginning. So we also got to give input on the shape of the building. So now you can see why it was called the Diamond Building, because it looks like a diamond. But this was not because we wanted it to look like a diamond necessarily. But this was because we looked at the sun path of Malaysia, and we realized that the sun sort of goes straight overhead. So if we tilt the facades to the north and the south by about 25 degrees, then we could fully shade these facades from direct sun. And then we could get in the diffuse daylight, which is very good for daylighting. And then for symmetry reasons, it was decided to do the same on the east and the west facades. At the same time, we wanted to push for energy efficiency in the, for daylighting in the entire building. So therefore, a central atrium was introduced, and this would allow daylight also to come from the center of the building as well as from the perimeters. And here you can see some illustrations, and these are actually from Nirmal's book back in 2012. Thanks for those illustrations. So here's a picture of the atrium, and it's maybe a little bit difficult to see, but we actually have different floors, window treatments. So at the bottom floor, you can see there's like a double high window, and these windows then become smaller and smaller as you go up in the atrium, because the higher you're up, the more daylight you have. So you don't need such a big window. So we would rather just have a white band of wall that could then reflect that light further into the atrium. And on these two floors, you can see the white color is slightly different. So here we have a special Tannenbaum panel that helps to reflect sort of semi-specular, semi-mirror panel that reflects the light across the atrium, and it's shown on this illustration here as well. So it basically reflects light into the two lowest floor levels where we need the daylight the most. So this building had a measured energy consumption of well, now it has dropped a bit more, so it's about 63 at the moment. So it's basically very much lower, about a third the energy consumption of normal office buildings. The building also has some solar panels, which you can see up here, but this is, I would say, easy to do, and that's not the trick to getting a building with a low energy bill. And you can also see the yield to the overall energy consumption is relatively small, about 10% of the consumption. We also looked at the additional cost that was spent to make this building energy efficient, and that added about 3.2% to the construction cost of this building, and that means that that would be paid back in less than 3 years. One of the innovations of this building was the way that we cool. So we embedded these pipes. It's a plastic called PEX pipes. So you can bend these pipes, and they are basically laid in the reinforced concrete slabs. So before you pour the concrete, you put these pipes in, and then you pour the concrete, and then these pipes get embedded into the concrete. So 40% of the cooling of the building comes from these pipes, and this cooling is done at night, which I'll talk about a bit later. These pipes can only do the sensible cooling and not the latent cooling, so that means they can't dehumidify. So you still need normal air conditioning to do the dehumidification. Maybe I'll just go back. So what you can also see on this illustration is the daylight system. So it's a split window design where we have a light shelf that has like a mirror reflection. And then we have a fixed louver that's tilted 35 degrees upwards. So that means that the light hitting this light shelf will then travel more or less parallel to these louvers and onto the ceiling. And you may ask, why do we need this louver? Well, in the tropics, the sky is very glary. So if we didn't have this glare protection, then people sitting inside the office looking out through this window out onto the bright sky would find that very glary, and then they would pull the curtains on the first day of operation, and then this daylight system would have been killed off from day one. So getting the glare, addressing glare in the right way is actually the key to a successful daylight system. So here you can see where we ran some ray trace simulations where you can see the light coming through the light shelf here. And also the windowsill down here, we also chose to in a white color, which also helps to reflect the light into the ceiling. So you can see from this photo, the ceiling is actually quite bright. And that means that these suspended ceiling lights don't have to be switched on most of the time. In fact, in the text here, you can see the measured lighting consumption during office hours is only 0.9 watts per square meter. So that is much lower than the code requirement. Typically, you maybe install 9 watts per square meter, something like that. So it's 10 times lower. So that's a very good saving. Here's some photos of this light shelf design. And on the middle photo here, you can see we deliberately designed it so the windowsill protrudes about 300 millimeters further than the light shelf. So therefore, you can easily walk on this windowsill, take out a few of these louvers and go and clean the light shelf with a cloth when needed, because of course some dust will accumulate over time. So instead of going and replacing the light bulbs, because the light is very rarely on, you just go and clean the light shelves instead. Another light feature in this daylight feature in this building was this roof light, which was at the deepest part at the top floor. And most people think that, okay, it's an electric light because they know they're deep into the building. And once they walk to the sofa and look up, they're surprised to see, wow, it's daylight coming in. Again, we designed it so we just take in the diffuse light. So we don't get the very harsh and warm direct sunlight. For the floor slab cooling system, we did some measurements because this is quite new here in the tropics. So one measurement is shown here, which is measuring the cooling that is delivered to the building over 1 week. So the blue color graph, that is the normal air conditioning in the air handling unit and the ducts. So this is during the daytime. The red one shows the floor slab cooling. So let's say we take Wednesday. So on Wednesday, around 7 in the morning, the normal aircon starts up. But the night leading up to Wednesday, so starting around 10 p.m. at night, so that's Tuesday night, 10 p.m., we had actually already started the slab cooling system. So that means throughout the night, we are running water of 18 degrees through these slabs. And we are basically cooling the concrete slab down, the floor and the ceiling throughout the night. So come 6 in the morning or so, we switch off the system. And then this cooling is slowly released to the space passively during the office hours. So if we had not had this floor slab cooling system, then the normal aircon cooling load would have been about 40% higher. So the advantage here is that we can shift, in this case, about 40% of the cooling to the nighttime, where you typically have cheaper energy rates. And we can also help to reduce the maximum demand of the cooling because we have a lower maximum consumption because it's spread over the 24 hours. And floor slab cooling, because you don't need to chill the water all the way to 6 degrees, which a normal chiller does. But in this case, you only need to cool it to about 18 degrees. So that means your chiller can actually run twice as efficient because it's the temperature of the lift is smaller. So therefore, you can actually save a lot of money on this slab cooling because you can benefit from a more efficient chiller, and you can consume the energy at night where the energy rate is cheaper. The picture on the right here shows the thermographic image of the slab. So you can actually clearly see that the pipes here are delivering cooling to the slab. So this is taken at night when the system was running. So a lot of people ask, don't you have condensation when you cool down the structure of the building? And that is definitely a risk. So that's why this system is not suitable for any building, and especially residential where you often open the windows. I wouldn't recommend it. But for this kind of office buildings where windows are typically not opened, there are some windows that can be opened, but they never are. It's okay. So we actually did some quite interesting measurements, as you can see on the graph below. And this was during a 6-week period where there was a change, there was a handover of the building to a new facility manager. And then they started operating the system in a manual way, and then everything went haywire. So we actually have some very interesting data that shows the system running during correct operation, which is this one called typical week. And then we have the week before that, where they switched over the system to manual operation. So instead of feeding 18-degree water into the slab, they took the normal chill water at 7 degrees and put that into the slab. And that's why you can see that the ceiling temperature dropped a lot during that week. And critically, it crossed the dew point. This is the dew point inside the office. So once you have something that's cooler than the dew point, then dew starts forming, just like when you take a water bottle out of the fridge, immediately you will have dew forming. So actually during these 3 days where we dipped below, there was water droplets collecting on the ceiling, and there was sort of, you could say, rain indoors. And that's why they quickly put it back to automatic operation. So during the correct operation, there's no problem. The ceiling temperature never gets down close to the dew point. But then maybe there was complaints or fear, and then it was switched off for the next 3 weeks. So you can see once they switched off, the ceiling temperature doesn't drop down every night, and is just allowed to sort of free flow. And therefore, the temperature in the building, the black one is the room temperature. You can see the room temperature also increases because it doesn't get that 40% cooling. 40% of the cooling was basically missing. So these 3 weeks were, the temperature was definitely warmer in the building than it should be, because 40% of the cooling system was cut out. So this graph actually captures all these different types of operation of this slab cooling system. So it's quite instructive, and if you just operate it normally, there's no issue with condensation. There's a video, 3-minute video. You can watch this on your own, and I'll be happy to make the slides available as well. So you can click that link. So let me talk about the next project, which is a case study of a retrofit project. And this particular building was 10 years old when we started this retrofit. And when you were inside the building, it looked even older. I mean, it was quite run down. But as you can see from this graph, we managed to get a substantial 53% energy saving measured after the retrofit. So it's quite a good case study for energy efficiency of existing buildings and the potential. This is the image before and after. It's the same room, and you can see it looks vastly different. One difference is that we removed this suspended ceiling, so we got a much more lofty space. Another difference is we managed to change the blinds. There was these vertical blinds hanging down that were always closed, so you didn't really have a view out. And the electric lights were on throughout the day. Whereas here we implemented a daylight system that I'll show you shortly, where we managed to reflect a lot of light into the ceiling, as you can clearly see here on the shadows up on the ceiling. So basically the electric consumption for the lighting dropped to near zero after this retrofit. And we also managed to reduce the noise level. There was a noisy street outside, and we managed to also improve the thermal comfort. So let me show you a few slides on this. So the problem of this existing office was that the facade was very leaky. So you had these typical cheap windows where they don't really close tight. They get sort of a bit warped. The gaskets are missing. So even though when the window is closed, you can literally look out through the cracks in the window frame. What we also found out when we removed some of the suspended ceiling panels was that there was no separation. There was no wall here. So that means what separated the aircon space to the outdoors was just these suspended ceiling panels and these outdoor panels above the windowsill, the exterior windowsill. And this was an open return aircon system. So that means the aircon air, when it was pulled back to the air handling unit, it happened through this ceiling space, and it was not ducted. So therefore, basically this space up here was also air conditioned. So it was not really ideal. I'm sure we lost quite a lot of cooling out that way. What we did from an architectural point of view, we left the existing windows in place, but we added a extra clear glass pane on the inside. So this way we sort of got a double glazed unit. So not only would it thermally insulate more, but it also ensured that we had an airtight window. And that would be also advantageous in terms of reducing the noise coming from the outside. And then, of course, we boarded up this wall above the window. So we had a sort of fully sealed facade to the outside. Then we also decided to remove this ceiling board. I'll show you shortly. But let me just first show you this window. So this was before, where we had these vertical blinds, and we decided to put in a Venetian blind instead. And this Venetian blind had some perforations. So if you closed it fully, like seen here, it's almost like a roller blind, so you can still look out. But normally you wouldn't do that. Normally you would leave it in place, something like this. And this is a great way to direct daylight into the space, because light can reflect off and be sort of reflected up onto the ceiling. And on this exterior window ledge, we placed a light shelf, which you will see in the next slide. So you can see that little red line here that represents the light shelf. So before and after is shown in this section. So afterwards, we had this light shelf. We had a louver that was mostly oriented something like 45 degrees, as shown here. So that meant that the daylight hitting this light shelf would be reflecting more or less parallel with these louvers onto the ceiling and further into the space, as you saw from the photo on the first slide. And then we removed that suspended ceiling, so you got a much loftier feel and a further throw of daylight. Because if this suspended ceiling had been carried through, then all this light would have been reflected down already around here, and therefore it would not have reached so far into the space. We did some temperature measurements before and after. So before is the black curve. It's maybe a bit difficult to read, but you can see that the aircon was switched on at 8 in the morning, and then it only dropped to about 26.5 degrees. So it was actually not a very cool office. It was a bit uncomfortable. And to save energy, they switched off the aircon as well as the lifts at 3 p.m. So I used to work in this office. So it was really hot to sit there, and you can see the temperature went up. So you're basically sitting in a non-air conditioned office towards the end of the day. So after the retrofit, we also changed the aircon system. So we put our own VRF on the roof, and we made this system. It had the demand ventilation control, so that means it was measuring CO2. So if there was fewer people in the office, then it would also reduce the amount of fresh air pumped into the space. So this was quite an efficient cooling system compared to the old one. And we could switch it on and off ourselves. So on this particular day, I only have 1 day of measurements from afterwards. But you can see we probably went out for lunch here. So that's why the temperature rose. And then coming back from lunch, we switched back on again. And then leaving at 5. So it was basically much more pleasant and much more efficient, because we saved 53% of the energy consumption at the same time. So there's a big potential for improving energy efficiency of existing buildings as well. Now I will talk about the sort of the main case study, I would say, and this is the factory in the forest. This is an electronics factory in Penang, and it's the mother company, Paramit, is based in Silicon Valley, but they have a factory in Penang. They've had one for many years. So the old factory was, I think, getting too small, probably, and they decided to build a new facility. And what was interesting about this client was that he wanted energy efficiency to be front and center of this project. As he expressed it to me, he basically wanted a cheap building. And to him, a cheap building is one that's very energy efficient, because he knew he would have to pay the energy bills. And it would therefore be very expensive to build a sort of ordinary factory and be stuck with these high energy bills for the rest of the duration of the lifetime of that factory. In addition to energy efficiency, he also wanted basically a factory with lots of fresh air, a good daylight, basically a conducive work environment, which I will show you now. Also means that it's a cheap building, because it really pays to look after your employees. So this is where we are getting towards this high performance. It's not just energy efficiency; it's also creating a conducive and healthy workspace. So what is the highest operating cost of buildings? I looked at my own office here in Malaysia, and as you can see, Salaries, the black bar, is by far the highest expense. We also found a study done here in Malaysia that had found that the average Malaysian has 66 unproductive days per year. And unproductive means that either you are sick, so you're not at work, or you suffer from what's called presenteeism. So that means you are present, but you're not really there, because you are not feeling well, you cannot concentrate, you are just not stimulated by your work environment, and you can't wait to get home. So this is actually a very high figure. In the UK, the figure is only 30 days per year that people are unproductive. And of course, that's also relatively high. So there's room for improvement, but especially in Malaysia, this figure is quite high. So 66 days means about a third of the days you go to work, you are unproductive. And as a company owner myself, that means that 1/3 of this black bar is basically money out the window, because my staff will be unproductive and they are not producing anything for the salary I pay them. So this is actually a huge expense. So therefore, high-performing buildings, they must provide occupants with a healthy, conducive, and stimulating environment that enhances well-being and productivity. And I always tell people this is actually the real benefit of green buildings. Sure, you will save on your energy bill, and that's great, and you can make a case for payback. But as you can see from the running expenses, rent, including utility bills, is a tiny sliver of the monthly costs. So sure, you can make some savings here, but what really counts is if you can make a building where you get a more healthy and productive workforce. So we made this cartoon where we call "Health is Wealth," and it basically shows the boss here at the end of the room. He's saying, "It looks like I'm going to have to pay more overtime payments because they have to finish some job and it's not done yet." And his staff are just sitting there. And this lady is thinking, "I would work much faster if it wasn't so stuffy in here." This guy says, "If only I can remember what I'm supposed to do." And this guy is saying, I'm gonna pretend I'm working. How can I work under these glary lights? So this is a real issue, and I think something that deserves much more attention. These are some figures that I copied from JLL, the big property management company, and they have reached similar conclusions. They have what they call the 3, 30, and 300 rule. So it's basically the expenses per square foot in dollars is utilities 3, rent 30, and payroll 300. So very similar to what we have found from our looking at our own expenses. And also from JLL, they compiled various case studies on this and found these numbers for the average increase in productivity for healthy buildings. So if you have individual temperature control, you will be 3% more productive. If you have improved ventilation, 11%, better lighting or daylighting, 23%, and access to the natural environment, 18%. So basically, you can, have significant increases in the productivity of your staff if you pay attention to these items. And there's actually a relatively new standard out of the US called the WELL standard. And this standard focuses only on the health and well-being of the building occupants. And interestingly, this standard was founded by the person who came up with the standard was an ex-Goldman Sachs partner. And he was basically looking at this huge waste of salaries, as I just described, because people are unproductive at work because they are spending their productive work life in a not such a productive work environment. So his approach was basically purely from the monetary point of view. Wow, what if we can spend a bit more money on making our buildings more healthy and conducive, and thereby actually saving a lot of money. So if you look at the categories in this tool, they look at the mind, for example. So what sort of stimulates your mind in a building? They also look at fitness. Basically going back to the old Greek saying that you have a healthy mind and a healthy body, right? So you need a bit of exercise and also nourishment. So basically, if you eat healthy food, you also feel better. So all of these things, which you don't normally see in other green building tools, are inside this WELL standard. So, oops. So if we look at the human health and what we die from, it's actually a very interesting website. You can click this link down here, and you can go and find your own country to see what, how we die and how our lives are marred with ills. So the unit is not deaths here actually, but what's called disability adjusted life years, because you don't have to die to necessarily suffer from it. It could also be that your life is impacted, but you're still alive. So if we look at the big three ones here for Malaysia, it's heart diseases, it's cancers, and it's lower respiratory infections. These are some of the big ones for impacting the human health. And the buildings we are in can actually help to address and alleviate all these three. So for heart diseases, for example, if you get some exercise, so for example, in the well standard, you have to have staircases easily available. So it becomes a real choice instead of you always taking the lift. Cancers can be triggered by the building materials we use and the air we breathe. And the same goes for these lower respiratory infections. And especially with COVID now, the building can, of course, help to reduce the risk of transmission of diseases. So if we go back to the mind, this picture is, I mean, you sort of automatically get a nice feeling when you look at this kind of picture. This is what we want. This is a kind of desirable environment we really like. But this is what we got. Many of us are in dense urban environments, and we just don't have access to nature in the way we really want. So we have this schism of spending a lot of time indoors in some quite urban setting, and what we really want is actually to be in nature, but we don't spend much time in nature itself. So this is where the built environment can try to strike a better balance, and for example, the importance of having spending time in forests is already an established science in Japan, where this thing called forest bathing is something that doctors can prescribe. So if you feel stressed out and you go and see the doctor, they might just say, okay, I prescribe you 4 hours of forest bathing per week. So you basically have to find the time, or you get a medical certificate to allow you time to go out and spend some time in a forest. And this is something that was actually started in Japan back in the 80s. And it's been incorporated into the health program of Japan. And there's various medical studies showing the benefits of forest bathing. So we asked ourselves, what if we bring the forest to the people, right? Save the trip to go to the forest. So this is basically what we did for this factory in the forest project. So these are actual photos from the building, completed building project. And I think it's after about three years, the bottom picture where the landscape has sort of really come up. And it's quite a nice experience to walk around in this forest. And especially when you compare it to the rest of this industrial park, which are these quite soulless, open industrial plots with not very charming factory buildings and not much greenery at all. So inside the factory, you have these kind of views. So this is an electronics factory. So this space is actually more or less almost like a clean room environment, but not entirely, but sort of along those lines. Yet you almost have the perception that you are in the forest. And this big window actually has, when it rains, you have these rain spouts. So you have a lot of rain coming down in front. So it's quite dramatic. That is then being collected by this pebble bed and going into rainwater tanks to irrigate the landscape when it doesn't rain. We did this anonymous survey with the staff in the factory, and we asked them, do you prefer the old or the new factory? The old factory was on Penang Island. This one is on the mainland. So transport, actually the factory owners were a bit worried they would lose a lot of staff because now they would have to travel much further, especially if they lived on Penang Island. But 90% preferred the new factory, and they lost very little staff when transitioning to this new factory. So that was also a good surprise, and maybe the nice conducive environment of the factory played a role in increasing the staff retention as well. This is a picture of one of the many roof gardens. This photo is taken in the morning. So you have the early morning sun streaming through because east is over here. But once you reach noon, so where the sun would basically be directly overhead here, you can see these louvers will then block almost all the direct sunlight. And then in the afternoon, when the sun moves over to the right here, then you cannot see the sky. And that also means the direct sun is not coming through. So we basically deliberately designed these louvers to block the direct sun in the hottest time of the day, namely from about noon and throughout the afternoon. So this is actually a green roof space that is usable because it's actually very pleasant. And I've tried that myself. I was up on this roof on a hot afternoon, but I didn't even think about it. It felt very pleasant. And until I looked sort of beyond the roof, and then I could see, wow, the sun is really full on outside the plot of this factory. And I realized, okay, but I feel perfectly fine because I was in complete shade and I had this breeze coming through. So I always like to say this is a roof garden that is actually usable because it's thermally comfortable to be there. If you don't have this kind of shading, then often it's too hot, and these roof gardens are not used very much for office buildings. This is the canteen. So also a very nice space, and this forest has really grown up now, so it's much more forest-like. And again, it's under this big canopy roof. So this is a morning photo where the sun comes in, but come lunchtime, then you are in a much more shaded environment. And this is in the office block, in the central atrium. So there's just lots of greenery, and you are really in a forest. So this really gives a nice peace of mind to many staff. And the other day I happened to see on LinkedIn, one of the Paramit staff, I don't know this lady, but she basically posted this picture, so quite similar to this one, right? And some other photos from the factory. And she wrote, working in a good environment is a blessing. Grateful to be surrounded by green environment. Never imagined that a factory can be this beautiful. And after 6 days, when I saw the post, I could see that there was already almost 500 likes and 52 comments. So lots of excitement about this nice factory environment. And to me, this is almost sort of the best kind of praise, because it comes from sort of just ordinary staff, and also to see the very positive reaction online. And this is another benefit of having this kind of high-performing building, because the staff are happy, they are proud to work there, and you will get a much better staff retention. I'm not really specialized in staff retention and this kind of thing, but someone told me who works with this that the staff retention is actually quite an important economic factor for a lot of companies. So if you don't have good staff retention, it can be sort of a big expense, amounted to about 9% of your running costs, because you will have that cost of retraining new staff and all that. But what is the benefit then of having this kind of happy staff that really likes this view? So it's of course difficult to measure exactly what is the effect on productivity of people, but there are some studies that have been done, and one study was done in Sacramento in the US, in California, and this was by a call center company that had several call centers in California, and they realized when they looked at the numbers that those call centers where the employees had a view out of the window, these employees were able to take 6 to 7% more calls per day than employees who had no view. So call centers are great for this kind of measurements, because the type of work is very easily measured, right? The number of calls per day, very easy to measure. So then they looked into the matter, and then they found out that if they were to retrofit the other call centers, then that would, to give everyone a view, that would cost about $1,000 per employee. But because salaries are the main operating costs, this would have a payback time of just 4 months. So the case is very clear, and this is sort of you would say scientifically measured from this call center example. So I'll get back to the and the closing of this presentation. I'll get back to the this sort of productivity benefit, but first I'll just talk a little bit about the design of the building, the green design of the building. So it was a combination of passive design and active design features, and for this building, and I think it's it's the first project I've had where the client actually looked for the environmental engineer first before looking for the architect. So I was the first one on board this project. The client really liked the kind of work we do, where we optimize energy consumption, and he said, "Great, you're on board. You're doing exactly what I'm looking for. Now help me recommend the architect." So I basically recommended 3 different architectural companies that I know here in Malaysia, and that I know do good work, and that I know are willing to listen to people like me, where we can have back and forth on the performance of the building. So that becomes incorporated in the design. And then there was a small architectural competition among those 3 architects, and we worked a bit with those, but we were not leading the design, but we would sort of feedback what could be improved in terms of designing with the climate. And then a winner was eventually appointed, and then we took it from there. So these are the best projects where sustainability is not an afterthought, but where it becomes one and all. I mean, it's an integrated design from the very beginning. So for this factory, the diffuse daylight was something we said, this is how we're going to light this factory. So the factory has these, yeah, you'll see it later, but these roof lights that are all pointing towards the north, where we don't have too much direct sunlight in the sky. And then we have this huge lower roof as well over the office block. So it was basically all about trying to block the direct light and making use of the diffuse daylight. Then we also, of course, had lots of greenery, and we implemented a floor slab cooling system, which meant that the whole factory slab had to be ice insulated. And we did some optimizations on that, which I'll show you later. And we also made sure to have some kind of stratification of the energy, of the temperature in the factory hall. So we had this low emissivity ceiling, so the hot air could sort of stay on its own up under the roof lights without entering the aircon zone below, and without radiating that hot temperature down to the cool floor. And then we harvested the rain for irrigation purposes. So for the daylight, we ran a number of simulations, and the idea was basically to take in the light from the north part of the sky. So only parts of the year when the sun sets to the northwest, we get some direct light. And it was not allowed to have any streaks of direct sunlight on the factory floor. So therefore we introduced these panels. So all daylight coming through would be bounced off this white plasterboard panel and then diffused into the factory. So the original design had lesser roof lights, but our simulation showed that we needed more of them, or they had to come closer together to give sort of a nice even light level. So this is the final design you see here, and this is a photo that we took at 2 p.m. on a sunny day before they moved in all the factory equipment and with all the electric lights off. And you can see we get a very nice diffuse light level at about 600 lux. So just nice, because in a factory you need a bit higher light level because they're doing electronics, so they have to sit and check these electronic parts. So yeah, so the daylight system worked quite beautifully. We did some glare simulations as well. So this slide shows the strength of simulation, because this image here on the left is a simulation, and the image on the right is a photograph when it was actually built. So you can see it's quite similar. It's not exactly the same view. So therefore, for example, this window is appearing, which was not in the simulation. But basically, you can do a lot of trial and error and prediction with simulation. So once the factory is built, there's not any surprises to be dealt with. This particular window was a bit glary, but the idea was that the extensive landscaping along the perimeter of the factory would come up. So this was only a temporary problem, and some blinds were put in place to deal with this temporary glare issue. And we also published a paper on basically coming up with the first tropical glare formula. So you can, download that paper, or I think you have to pay for it, but I can, if you approach me, I can send it to you if you're interested. This paper will be incorporated in some of these simulation tools eventually on the market. On the active design side, some of the features that we put in was a dedicated outdoor air system. So that means that the outdoor air was, all the dehumidification was done in that system. And there was also energy recovery done. So some of the exhaust from the factory, we recaptured some of the dryness from the air inside and transferred it to the incoming air. So this way we could save about, I think it was 30% of the energy for the treatment of the outdoor air. So after the dedicated outdoor air system, then that air that had already been fully dehumidified then went into the normal so-called air handling unit, and this one would just sort of recirculate the air in the factory and ensure the right temperature. The fresh air requirement is quite high in these kind of factories because you have various substances going into the air from a production facility. So we followed the ASHRAE figure for required air, fresh air supply. And for cooling, we put these slab cooling in this concrete slab for the entire factory hall, as well as for the office spaces. So this is where 1/3 of the cooling was done this way. And this factory had sort of various ovens that were creating a substantial amount of heat. So heat is basically sensible heat, so that can be cooled quite effectively with sensible cooling from a floor slab cooling system. So this is how this floor slab cooling system looks in reality. So it's basically these kind of pipes that go into the concrete slab, take some loops, and come after about 100 meters, and come back. Because if you go beyond 100 meters, then the pressure drop becomes too high. So basically they go in at about 17 degrees, and then they come back at about 19 degrees. So they give off cooling, and the surface of the floor is about 20 or 21 degrees. And this is also high temperature cooling, just like in the ST Diamond building you saw just now. So we could basically get a chiller COP of 10, which is quite high. High efficiency. So we did some interesting studies on the insulation required for this factory, because we are basically cooling the whole floor. So we built up a model like this with all the soil below the factory, and we had a look at how to best insulate the how much insulation should be put in the floor. So as a initial estimate, we said, okay, we put 50 millimeters of insulation in the whole floor, and these are the chilled water pipes. So we didn't go all the way to the perimeter, so we stopped short about 1 meter, because we also didn't want to lose cooling through the wall to the outside. So if we simulate this, and this is the simulated temperature in a sort of steady state scenario, which is realistic because this factory is 24 hours air conditioned, because these electronics have to be kept at a certain humidity level. Then you can see this is the kind of temperature profile we get. So over time, we will actually get a cooler temperature in the ground below the factory. So you might think, wow, this looks like we're losing a lot of energy, but mind you, this might only occur after I don't know how many years. So what you really should be looking at is what is the heat flux, what's the rate of cooling or going into the ground, or rather how much heat is coming from the ground into the factory. So if we look at the heat flux, then this is how it looks. And what was interesting to observe is that it's really at the perimeter where we have the high heat flux. As you can see here on the scale below, the red and the white color is the highest heat flux. And the reason for this is that this is where we have the relatively cool temperature of 17 degrees. And right on the other side of the outdoor wall, we have the ground temperature, which would be about 28 degrees, and the outdoor temperature. So the heat from the outside doesn't have to travel very far to get to the cool floor indoors. Whereas if you are in the middle of the floor here, that 28 degrees would have to travel through a lot of soil before it gets to the cold floor. So it was actually all about optimizing the insulation in the perimeter. So that's what we then decided to do. So we looked at the first 4 meters of the perimeter of this factory, and we looked at okay, this is the with the 50 millimeters of insulation throughout this line or throughout this insulation layer. This is the kind of heat flux we get, and you can see that it's not really ideal. So we wanted to, maybe it's better illustrated here where you see all the arrows that represent the size of the heat flux. So it's really right here at the perimeter where we have the highest heat flux. So we tested out these 16 different variations, and we narrowed that down to about 3. And then we looked at, okay, what if we insulate around the perimeter about 200 millimeters thickness. And then once we get further in, 2 to 3 meters in, we reduce that to 150, then 100. And then the whole middle section of the factory could actually make do with just 25 millimeters of insulation, because the huge ground layer also helped to insulate. So while we would be insulating more at the perimeter, we actually saw an overall saving of insulation, because the big center part of the factory, we got actually half the insulation. We also looked at what if we dig down vertically 2 meters down and put like an insulation layer like that. So we force the heat to sort of go deeper into the ground before it can get to the cool slab. But this was not practical and probably also a bit expensive, because the groundwater level was quite high for this site, and insulation would then float up and so on. So we didn't do that. So we basically did something along these lines. I forgot to put in the final solution, but so it's a little bit more complex than you see here, but the principle was the same, that we increased the insulation at the perimeter, and then we could reduce the insulation at the for most of the factory without increasing the cooling loss through the slab. So another interesting achievement with this factory was the sizing of the cooling system, because for most energy efficient buildings, there's a bit of guessing involved from the from the mechanical engineer as to how big should I size the cooling system. And often you will have some kind of safety factors, and almost all buildings have cooling systems that are oversized, sometimes by quite a lot. And especially for factories where it's anyone's guess how much heat is actually coming from these machines. The original cooling system proposal from the mechanical engineer was more than 900 refrigerant ton of cooling. And we said that's too high. And of course, we did the detailed simulations, and we also had readings done from the old factory. So we knew approximately how much heat was generated by this manufacturing equipment. And then we also had this split cooling system where about a third of the cooling came from the slab cooling. But the mechanical engineer was not really, I mean, he also had some calculation software, but he couldn't really incorporate that in his software. So he was a bit uncertain whether it was correctly simulated. Another thing he couldn't simulate was the thermal stratification of the space. So the fact that under the skylights for the factory, there would be this hot air and just sitting there and not mixing with the aircon zone. So that's why in the end his estimate was that we needed this big a cooling system, and we said no, we only need about 400 refrigerant ton. So he agreed that our model was much more accurate than his was, and that meant that for this building we could downsize the cooling system substantially, and that saved $1.2 million in capital expenditure for the cooling system. So that's already a very good saving, because it reduced the cost of the building. And I calculated that in terms of our fees for this job, our fees were paid back 16 times over right there, because we managed to downsize that cooling system. But this kind of scenario is quite common, and I saw some data from Singapore as well, from office buildings, where, if I remember correctly, the average office building in Singapore has cooling systems that are about 3 times too big compared to the normal cooling load. But the biggest savings actually came from pushing efficiency and getting a factory that had a 40% reduction in energy, which the client is very happy with. So that means for the next many years, he will have a much lower energy bills than would otherwise have been the case. And it's difficult to reduce factory building energy consumption, because these big ovens, we cannot really do much about it. These are bought from some manufacturer, and we cannot, it gets a bit complicated once you try to alter the manufacturing equipment. So about 40% is pretty good. So getting back to the overall picture for this factory and the sort of the ROI, or the payback of a high-performing building, I'll just finish off with some slides on that. So, for example, on this anonymous occupancy survey, we compiled those answers, and you can see that we asked them in an open-ended question what they like about the building, and when we pooled those answers together, basically about a third said they liked this contact with nature, about a third of them said it was a beautiful building design, so just pleasure to be in this nice architecture. And 16% said it was a conducive work environment. So basically, quite good feedback. And then there were some other compliments as well. We also asked them what they didn't like about the building. It mostly had to do with that some of the spaces were maybe a bit too small, like changing rooms. And some even had seen a snake at the factory. So there's sort of too much nature maybe for some people's taste. But basically, I think it was about a third of them said they had no comments. So a third said there was nothing they didn't like about the building. So that was also a good feedback. And then we got these kind of nice statements, like someone said, it's the best place I've worked. The greenery around the factory is simply amazing. It gives us a peaceful feeling. Another one said the beauty of the natural de-stress while working. Someone also said it was like a second home, this factory. So all these, good comments. So if we go and look at what about the payback time? So I made this chart, and if we look at energy efficiency only, because this building definitely had some additional costs, as you can see, with the big louver roof, extensive roof gardens, and so on. So if we only look at energy efficiency, reduction of energy bills, then the payback time would be about 8 years. Which is still okay because this factory will be operating much longer than that. But then if we factor in the productivity increase, so if we use that figure from the call center where they saw a 6 to 7% increase in productivity, so let's just say 6% because that's conservatively put, from having windows, and everyone has a window at daylight at their workspace in this factory, then you can see the payback time drops down to be between 3 and 4%. 3 and 4 years. But of course, this is not just a call center window. Here you're really immersed in nature. So if we assume that the productivity increases 14%, which seems to be the case. I mean, a reasonable figure from other figures out in the research and literature. Then you can see the payback time becomes 2 years. And that's just from productivity increase. Then you don't even count in the staff retention, which I mentioned before, which should also be added to this. And of course, you get this improved image because the client also uses this amazing building as a good way to, when they bring customers in, to sell. And then, of course, they're getting a lot of free publicity because this building, I think, is quite famous now because the environment is so interesting and out of the ordinary. So once you factor all these things in, actually just do it, and once energy prices increase because they are artificially low, we are not paying any environmental taxes in Malaysia. And of course, last week we were told by the climate people that now it's code red. We really have to get going. So of course we need to, for example, pay CO2 tax. So energy is also going to be more expensive, and that will only help to push the payback time down even further. So that was my last slide. I would also like to mention that there's a very nice book coming out, and there's a pre-sale going on at the moment until 22nd of August. So you can actually order this book on the Factory in the Forest It's 150 pages, hardback. So, and it's about, in pre-sale, it's $29 US. So, so if you're interested in that, you can go to this link and order a book.